I'm going to look at an expression for the acceleration for an object undergoing uniform circular motion. So motion is a circle, the speed is constant, that's the uniform part. So the position vector from the center of the circle to the location of the object is r1 at one instant in time, and then its velocity is tangent to the circle. So that's the vector v1. Let me come back and look at it just a little bit later. So a tiny amount of time has elapsed, and we'll have a new position vector that is rotated through an angle, small angle d theta, and now velocity vector, regardless of how I draw it, is perpendicular to the new position vector and is meant to have the same length. So the length of the vector v1 is the same as the length of the vector v2. If I put these two vectors tail to tail, I'll have v1 and then almost the same vector but rotated just a little bit, the vector v2, and there's going to be their difference, dv, and that difference is arising because the vector has rotated through an angle d theta. Okay? So the length hasn't changed, the direction has changed, and the direction is changed by going from rotating initially along this to along that. Now, let us look at the size of the acceleration associated with that change in the velocity vector. So acceleration is the time rate of change velocity, so dv dt. Well, the length of the vector didn't change. What did change is the direction that it pointed. So what we can say is that for uniform circular motion, the acceleration is v times the time rate of change of this angle, okay, which that is the angular velocity, omega. Okay. We have a relationship between v and omega, so velocity tangent to the circle and the angular velocity of the object rotating around. We know that v is equal to r omega. So we have between this relationship that the centripetal acceleration is v omega and the relationship that v is r omega, we have three relationships we can use, whichever one is most convenient given the information that you have available to you. So for the centripetal acceleration, we can say that the acceleration is v omega, or we can eliminate omega as being v over r. And this is probably the form you're most familiar with seeing. Centripetal acceleration is v squared over r, or we could have instead eliminated the v by replacing with r omega. So if we have an object in circular motion there has to be an acceleration in towards the center of the circle. So if I were to draw in acceleration vectors, they point opposite to the position vectors. So there's A2, there is A1. For uniform circular motion, the length of those vectors isn't changing, just the direction that they point. And then how long is that vector? Say it's v squared over r, or if you happen to know instead radius and angular speed is r omega squared, or if you happen to be in a situation where you know linear and angular speed, that centripetal acceleration is v omega.